fact, have creatures on Earth which would go in that ocean and live very happily. They could be made, the life could arise in the same way as it's one of the ways that we possibly has arisen on Earth. This is a black smoker on the Earth's, the bottom of the ocean. We're very hot water, rich in the chemicals of life, carbon-based chemicals, come out of the bottom of the ocean, make what's called a black smoker. And in the vicinity of black smokers, we find chemistry which is suitable for producing living things. In fact, life first appeared in life on Earth 3.8 billion years ago at the earliest time it could have, possibly from this to one of the many other possible chemical pathways that have been identified as the way to develop life. There's usually much life around these smokers, life that has evolved to live in this kind of an environment. But there are already creatures in the Arctic, and this is one of the most beautiful creatures on Earth that very few of us have ever seen. It's called a comb jelly. It's a form of jellyfish. It's about 3 or 4 inches in diameter. It's not a tiny thing. This is the most common life form in the Arctic Ocean. It swims. It has these beautiful colors, which are produced by a diffraction gradient effect on its surface. And you could take these and plunk them down in the ocean of Europa, and they would thrive. So there really is a possibility that when we ever drill through the ice of Europa, we will find life there. Not intelligent life, not technology using life, but life which will evolve, will become increasingly sophisticated. One can't be sure if it could ever make a technology. But a very important point is never underestimate life. It is opportunistic, it is adaptable. If there's a way to improve itself and to survive, it will do it. And we see that all across the Earth and all through our history. This is the species you see here. And this is another picture of one close-up of the comb jelly, Mertensia ova. Now, another place we've discovered where there could be life, to our surprise, is a satellite of Saturn, much farther out from the sun. This is the satellite Titan, which actually has an atmosphere with about the same atmospheric pressure as the Earth, but a different chemical composition. It doesn't have the nitrogen, the rich nitrogen we have on Earth. It has hydrocarbons, stuff, which is more suitable for producing life than the atmosphere we have here on Earth. And we've seen now from our spacecraft close-up pictures which show these areas which turn out to be very flat and are almost certainly lakes of hydrocarbons. You get here would solve our energy shortage, put OPEC out of business, because there's just almost an infinite supply of gasoline, butane, and propane here in liquid form on the satellite Titan. Now the temperature is very low here, about 100 degrees above absolute zero. It's about minus 350 Fahrenheit. But the chemical processes can occur here, and there could be life which actually thrives at low temperatures like this. So this is another prime place for us to search. Another one recently discovered is the satellite Enceladus of Saturn. Apparently covered everywhere with ice, and yet we've seen a very strange thing in near these cracks you see here, which are called tiger stripes, which is geysers of water coming off the surface, which you see here. So it says there's actually liquid water at the surface of Enceladus, and it creates geysers. These actually go 50 feet above the surface. And so we've now found a total of actually 7 places in the solar system where conditions are right for life, when originally we thought there was only one. And that's been an extremely great development in the science we now call astrobiology. Now, whether a technology using creature could ever evolve in these places is very problematical. But again, never underestimate life. If you come away from my talk tonight with any particular fact, it is life is adaptive and life is opportunistic. And lastly, I want to mention, not lastly, and almost lastly, in this part of the talk, I wanted to mention the M stars again, where this is an M star. This is perhaps a planet of an M star. much like the Earth with water. Some of them will be so close to their star that they keep one face to the star, just as our moon keeps one face to the Earth. That's a result of tides on them. In that case, you have a very hot place here and a very cold place here where the star never shines. There's never anything like sunlight at this place. What happens is you get very powerful winds that blow from the hot part here back to the back, and then it recirculates around. And you need that circulation to bring enough heat back to the dark side to keep it warm enough that the atmosphere itself does not freeze out. But what that means is you have a tremendous range of temperatures, from very high to almost freezing, and somewhere in between, Goldilocks, the temperatures are just right for life. This tells us that, in fact, M stars may be one of the most promising places to find life. Some of them have orbits which prevent them from keeping one face towards their star, and that's all right too. So in fact, M stars are perfectly good abodes of life, and they should not be searched, although they've not been on our search target list for a long, long time. One other objection to life on M stars, which I thought from day one was pretty silly, has to do with the fact that these stars are known as flare stars, which means they get very much brighter for short times. They sometimes double in brightness for an hour or so, usually less than that, but up to an hour. And wouldn't that intense heating and light kill the life? Well, remember again, life is adaptable and opportunistic, and life would find a way to get through these heating crises. And in fact, we have one creature, at least on Earth, that's already adapted. Put it down on one of these M stars and it would be perfectly happy. I wonder if any of you thought of what it is. It's a creature which you're familiar with. It's not some mysterious exotic thing which lives in the depths of pools in Yellowstone or something like that. It's this. Star lights up, turtle just pulls into its shell and waits out the bright light. And if that's not enough, an even better way for this thing to survive is to be in the ocean. Because once you go in the ocean or into a body of water, more than about a meter down, everything works very well to protect you. You're protected from the radioactive radiation which comes with some of these flares, as well as the heat pulse that it comes from. So there's no doubt, I think, that on M stars life could evolve and defend itself against that problem. And lastly, I'm going to mention an object which is very tantalizing and interesting, which is the thing which is depicted here. What is this? It is what was the planet of this star. What we have learned is that when the solar system, planetary systems form, there's chaos. The planets which are forming often pass nearby one another. They mutually attract each other with their gravitation, and one is sped up while the other is slowed down. And if this happens a few times, the planet can be given enough energy that it will actually escape its planetary system and go into the interstellar space. And the fact that some of the systems we found show that evidence of that. And indeed, in our own solar system, if you tried to put it on another planet, it would create this kind of chaos which would in fact lead to the ejection of the planet. What this is telling us is that the Milky Way must have many, many planets no longer in orbit around a star, but moving freely through the very dark, cold reaches of the galaxy. We call them rogue planets. This is a very young one, so it's still got a lot of volcanic activity. Wanderers, or nomads, those are all names that have been invented. None of those has been adopted yet for them. They must be there. There's no doubt they're there, but we have never seen one, and the probabilities are that with our current instruments we never will. And yet they must be out there. And if they have a deep enough atmosphere, they retain enough heat that they can, for 4 billion years, have temperatures suitable for liquid water and could give rise to life, including complex life like our own. So even civilization today exists even between the stars, which is a very startling consequence of all this. Now, what do we do about all this? What are all the things I just told you encourage us to search? We know now many more places where there could be life. We know that life is very adept at adapting to situations, of evolving, of becoming complex enough, and with enough abilities, manipulation of tools and such to create a technological species. What have we done? Well, we've sent messages. Now, this is the Voyager spacecraft. There are two of those. On them there is a gold-plated box you see here. And in that box, this is the box, there is a golden record. The cover of the box tells you what to do with the record which is inside. This is the very much like the 60 RPM phonograph records that were popular back in the 1970s, and that's what's in here. It's really one of those. And it has all these instructions as to how to play the record. We also included a stylus for the extraterrestrials in this one. There's instructions here as to how fast to turn the record, and it shows actually what the first picture on the record is, because there is a group of pictures on it. What's on this? 115 television quality pictures of life on Earth, greetings in 50 human languages, long series of recordings of the sounds of Earth, from the sounds of falling rain, lightning, to the cry of a baby. Greetings from UN delegates, and also 3/4 of the record is actually music, Earth's greatest hits. And it includes Brahms, Beethoven, but also Blind Willie Nelson, and a lot of very beautiful ethnic music. It does not contain any Beatles music, despite our efforts to make that possible, because the Beatles absolutely refused, on the basis that they don't grant their copyright to anybody, not even to send their music into outer space. So they got cheated. They are no longer part of this record, which is perhaps, will be perhaps the longest lived product of our civilization. This may exist after the sun has expanded and destroyed the Earth, and perhaps that we no longer exist. This is what the record looks like. But sending messages is something that you only do if it doesn't cost anything. And this was a hitchhiker on a spacecraft, and there are 4 such things. They cost almost no money. They're just riding free on the spacecraft. If you're going to have a limited amount of funds, as we do in SETI, you want to use them in a way which gives you the best chance of learning of extraterrestrial life. And to us, that is still trying to detect other civilizations and listen to their transmissions and learn about them from that. Ideally, we would like to capture their television, other signs of their existence, and learn about them by that means, rather than by sending messages, which, as in this case, because of the slow speed of the spacecraft, as I mentioned, this is not going to reach the vicinity of a nearest star for 500,000 years. We've now broadened our view as to what we should search for, because we recognize that radio is not the only thing. We may be very good at radio, but what of other civilizations? Might they be good at something else? We know that electromagnetic radiation is a prime candidate for interstellar contact and messaging, but is radio the one that's used? Perhaps there are infrared cults or something, transmit infrared signals. And so nowadays we have moved on searching for optical signals. And one search is one we at SETI Institute run at the Lick Observatory near San Jose, California. We use a 40-inch telescope. And we have a very simple receiver, which is in this box, which is hardly visible, for those of you in the back of the room. And this is searching for flashes of light from high-powered lasers. Now, why does that make sense? It's because we on Earth have invented extremely powerful lasers, not to signal with, but to use in nuclear fusion machines which will produce clean, abundant power by fusing hydrogen into helium, as is the source of energy, as is the means by which energy is produced in the stars and the sun. This is a very major endeavor which is taking place in Europe, in America, in Russia. And one particular approach is called inertial confinement, where you take a bubble of gas, tiny bubble, about the size of a BB, and if you can heat it to about 100 billion degrees, almost instantly, it will be hot enough that the gases inside, hydrogen gas, will fuse and produce much more energy than you put into it. It has to happen almost instantly because when it's heated, it creates a huge pressure and it tends to just blow itself apart. You have to make it hot enough to cause the fusion reactions to occur before it can explode and dissipate into the surroundings so that the fusion cannot occur. That means you have to heat it in about 1/1000th of a second. You have to heat it by 100 billion degrees, 1/1000th of a second. To do that, lasers have been constructed, lots of them, which in the United States make a peak power for 1/1000th of a second of about 1,000 million watts. 1,000 million watts. That is about 100,000 times the total electric power production of all the electrical plants of Earth, believe it or not, but it's true. Not for long, for 1/1000th of a second it does that. And actually in the American experiment, which is being done at the Lawrence Livermore Laboratory in Livermore, California, it takes 160 of these lasers all zapping the bead at once to make all of this work. They are just about to do the first experiment where they do that. The thing has been constructed. It's a mammoth machine. The whole thing fills an area the size of a football field. But that's what's going on. But to us, the important thing is they've caused us, been able to show that such lasers can exist, which means other civilizations can have them. And if you take the pulse from one of these lasers and focus it with a 10-meter telescope as it exists on Mauna Kea and other places on Earth, the flash is so bright that it's brighter than all the light of a star. So that if you're looking at the right time with a sensitivity, a sensitive detector which can detect a 1/1000th of a second pulse, you could detect the existence of a civilization. And it turns out a telescope this size is enough with the detectors we have. And so there are searches at Lick Observatory at the University of California, Berkeley, and at Harvard. Well, this is the Lick system again. This is the detector. The whole thing is very simple, by the way. It just uses off-the-shelf components. This was all put together by an undergraduate student, here she is, as a senior thesis project at University of California, Santa Cruz, and she's presently a PhD at UC Berkeley. There's also a very new and very powerful search system at Harvard, shown here. It has a mirror that's 1.5 meters in diameter, and reflects the light up here, and the light goes out to a system of 64 detectors. And they're very proud of it because they claim, I'm not sure this is verified, that they have this is the largest telescope mirror east of the Red River. Now, I don't know, it's just west of the Red River, which makes that boundary, but that's the statement that's made. So we search for optical signals, but still, to most of our minds, the most promising approach is the one that dates back 50 years now, which is to search for radio signals. And there have been more than 100 searches since the search of 50 years ago. Many of them done to what is the world's largest radio telescope, the Arecibo Radio Telescope in Puerto Rico. This is what it looks like these days. It's got a reflector that's 300 meters across, 300 meters across. These towers are 555 feet high, a little taller than the Washington Monument. It supports the energy collecting apparatus here in the center. This, by the way, is as large as the next largest telescope, which I'm sure you've heard of. It's called the Green Bank Telescope. It's the same size. This is, right here is the same size as the Green Bank Telescope, and it is suspended 50 stories in the air above the great reflector that you see here. This has been used for many years for SETI searching. It is the instrument that produces all the data that is used in the SETI at Home project, which some of you probably do. How many of you work with SETI at Home? Good, there should be more. This is something you do with your home computer free of charge. Just log on, go to www.setiathome.org, and they will send you free software, and you can search for extraterrestrial signals using data taken from the Arecibo telescope. This is the suspended structure, which, as I said, is 100 meters across. They're about the same as the GBT. In this particular dome, there is a radar transmitter which transmits a power of more than 1 million watts. And that signal, when focused by the big reflector into a narrow beam, has an effective power, a power so powerful that to duplicate it without the big reflector would require you to transmit 20 million watts. And that's again equal to the total electric power production of all the electrical plants on Earth. It's by far our strongest signal. It's a benchmark. It shows what a civilization can do, and this without much effort and much expense. That radio signal outshines the radio's emission of the sun by 1 million times. It's detectable by a similar instrument all the way to the center of our galaxy. This demonstrates that we really have the capability of looking very deep into our galaxy. Got more than half the stars in our galaxy for signals. This is the reflector surface. It's very large. It's 38,000 individual panels about the size of a dining room table, all set into place to an accuracy of about 1 millimeter. Now, other things have been very important in recent years. We've exploited computer technology so that instead of monitoring only one channel at a time, we can now monitor literally hundreds of millions of channels simultaneously. And of course, you don't have enough people, you can't pay enough people to look at all of those channels to see if there are any signs of signals. So there's other equipment built which automatically searches through the captured signals to see if anything looks like an extraterrestrial radio signal. This equipment that you're looking at here was used for many years on a 140-foot telescope here at Greenland. This shows you a typical screen. Each horizontal line is 1 second's worth of data. There are about 600 channels across here. You see bright spots. These are channels where there was more than the average power, most of it due to noise. And as time goes on, actually this is the earliest time, as time goes on, coming up here, and you see this line, which is in fact an intelligence signal from one of our spacecraft, the Pioneer 10, when it was beyond the orbit of Pluto, easily detected. The total transmitted power there is a few watts, and the line is sloping because there's a Doppler effect introduced into the signal, in this case by the rotation of the Earth. We use this as a very powerful tool to distinguish signals that are truly from space and not from interfering objects sitting on the surface of the Earth. Now, recently, SETI has recognized that it needs a dedicated instrument because there are instruments like Arecibo, like the GBT, other large ones which we would love to use, but they are not lose, that's for sure. I already tried that experiment here. That was a bad result. We need much more observing time. We need a dedicated thing so that we don't depend on being guest observers. At Arecibo, at best, they get 20 days a year, and that's just not enough to make progress rapidly. So what do? Years ago, we embarked on trying to build a very large antenna very cheaply, and to do that, we've done something which has worked well elsewhere in the world, which is used, instead of making one very big reflector, which are very expensive per square yard, if you will, of collecting area, use many, many small antennas and now exploit the power of electronics, of computers to combine the signals so that you duplicate the power of a single very large dish. And this is a prototype that the SETI Institute built in California. These are 14-foot antennas, as you see here. Very cheap. They only cost about $1,000 each. And here you see a prototype array of about 7 of them, which work very successfully. All the signals being joined together so that it simulated a dish which was square root of 7 greater in size than one of the single dishes. This, of course, has been carried out extremely well by the NREO, not here in Greenbank, but at the very large array in New Mexico, and is now being the basis of what's being done at millimeter wavelengths at the Atacama Desert with the Alamo project. So this is prototype, very inexpensive antennas, is all it takes. And this led to what's called the Allen Telescope Array, which is based on this concept, which is known in the community as large N, small d, large number of dishes, small diameter. And that's what the Allen Telescope Array is to be. It has antennas which are 6 meters in diameter, about 20 feet in diameter, and eventually there's to be 350 of them. That will give a collecting area about equal to that of the GBT. It's a partnership between the SETI Institute and UC Berkeley, and this shows you the actual antennas, which are in fact modeled on the GBT. They are offset Gregorian in the jargon of astronomers, which is what the GBT is. The GBT, this thing is on the top. In these antennas, it's on the bottom. It doesn't make much difference. So the fact that this doesn't look like the GBT is because the GBT is upside down. Of course, we can't do anything about that. The path of the radiation is as you see here. And here you see them being trucked from the dishes themselves, which are made in Idaho, being trucked to California. It's one of the nice things about small dishes is that you can make them in factories where they can be made cheaply, and then you can carry them places without great expense or special effort. Here's the construction underway at Hat Creek, California, which is the observatory of the UC University of California, Radio Observatory of the University of California. They're all being constructed in a tent. Here you see one of the dishes being assembled in the tent. And there it is. In each case, there's a special machine that comes and picks up the dish when it's ready, takes it out, and puts it on a pedestal, as you see here. It takes about 1 day to erect each dish. At the present time, there are actually 42 dishes. This is one glimpse of the system in California. And here is the latest pictures. And at the bottom here you see all of the dishes which now exist, which is 42 of them. If the system is working and doing as it should, with the signals being combined by electronics to simulate the performance of about a 34-meter single big dish. Eventually there will be 350, and that will simulate a 100-meter dish like the GBT. That's all the good news. The bad news is we've run out of money. So for now, there's no more construction going on. But there is an observation going on. Now, that's what we're doing. And as you can see, we're proceeding to follow the idea that radio is the way to search and detect other civilizations and to learn from them. Always in the back of our mind, the idea that we will look for the television of other worlds. Once we find a civilization, we can probably obtain the necessary funds to build a very large telescope necessary to capture television at a useful strength that we can produce the pictures and sound and all that. That probably, we are a guide who will take a system which is about 5 miles in diameter. That sounds like a lot, but it's actually, in cost, only about $100 billion. But it's probably worth every penny. But there is, in a way, a dark cloud on the horizon. As I mentioned, we always use ourselves as a benchmark, as a model for what other civilizations might be doing. There's nothing else we can do. We'd like to be able to psych out the extraterrestrials and figure out what they would be doing 100 years from now, but we can't do that. We know we don't know enough to do that. We have to use ourselves as a model. And for 50 years, we've had the ability to detect the strongest signals leaving Earth very easily, particularly the Arecibo signal. But now we see something happening which is causing our Earth to become less detectable. And of course, that makes us stop and wonder. The typical track of civilizations, they become very visible for 100 years or so, and then sort of fade from the scene. They may still be there. They may be thriving. They may have a rich civilization, and yet be very hard to detect. And yet we see forces and action in our civilization that are probably active in other civilizations, which might lead to exactly the scenario I just described to you. For example, what are you looking at here? You can't quite read the sign because the projector's not quite up to snuff. This says this is one of the stations of the North American early warning system. This is in Barrow, Alaska. It looks towards Russia. It's a relic of the Cold War. It's a radar, which there are 20 or 30 all across the north coast of Canada and Alaska that watch for aircraft and ballistic missiles coming from what was the Soviet Union, Russia. I wonder what these have become, because these have been one of our benchmarks too. Until recently, this was actually, other than the Arecibo telescope, the strongest signals leaving Earth. So what's happened as a result of the end of the Cold War? I actually took this picture. I went to Alaska with a spectrum analyzer, loaded it in the car, and just drove it up to this vital radar, which is defending all of the northern United States. And it was a surprise. There was no gate, no guard. Nobody even came out to see what I was doing. I got out of the car, set up my spectrum analyzer, measured the spectrum of this radar, and nobody cared. There wasn't even a guard dog. Where was the TSA when the country needed it? It's pretty amazing. I've found out since that, in fact, these are totally robotic. There's nobody there. So that even if there'd been somebody, there was nobody there to come out and say, what are you doing here? Well, it's kind of an interesting story. How did that, why is it that way? Any terrorist can come and blow up this thing and nobody will even notice. Well, for the experts in radio technology here, I'll show you the spectrum of this. This goes from 300 megahertz to 2 gigahertz. And this is now at Barrow, Alaska. If you make this same kind of spectrum anywhere in the States, you see signals everywhere. But in Barrow, Alaska, there's only this signal here, which is cell phones. Cell phones at Barrow, Alaska. And then this, which is that radar I just showed to you. And the interesting fact here is that this is no longer what it used to be with these systems, a narrow band signal present at only one frequency. It is spread over 50 megahertz. And if you watch it on the screen, you see the signals jumping around all over the place. This is called spread spectrum, frequency hopping transmissions. It's done with military systems to confuse the enemy and make it difficult for them to jam the systems. But what we see then is that this signal, instead of being very strong at one frequency, is spread over a tremendous number of frequencies. It's also weaker than it used to be, basically, because the radar systems have become more sophisticated and they can detect the targets they're trying to detect with less power. And so what used to be our strongest sign of our existence, other than Arecibo, has become this, and our present search system did not find this, particularly because it's spread out in spectrum. So one of the main signs of our existence has disappeared. But it's worse than that. The other main sign of our existence has been our TV stations, of which there are about 4,000. In most of the developed countries, the typical power of a TV transmitter has been 1 million watts. That's the UHF frequencies, 1 million watts. That's what it took for ordinary households with a rooftop antenna to detect the signal with enough intensity to give you nice clean pictures on your TV set.